Hello, this is Jack Jackson. Today we're going to talk about identities and conditional equations a little bit and look at some fundamental identities that we have from trigonometry. Now, an identity is an equation that's true for all values of the variable, or at least for all values where both sides of the equation are defined. On the other hand, a conditional equation is an equation that's only true for some values of the variable. For example, let's look on the identity side. Something from elementary algebra. 2 times parentheses x plus 1 is equal to 2x plus 2. That's a specific example of the distributive property, and that is an identity because it's true for every real number x that we can put in. Pick a number x, put it in on the right side and work it out. Put the same number in for x on the left side and work it out, and the two sides will be exactly the same. On the other hand, look at example 1 on the right side where it says 2x plus 6. Well, that's a conditional equation because that is only true under certain conditions. In fact, the condition that's true is when x is 3. If you plug in x is 3, you work out both sides, you get 6 equals 6. But you plug in any other number, let's say 1, 2 times 1 is 2, 2 equals 6, that's a false statement. So we get it's only true in certain cases. Let's take an example from trigonometry. Over here on the left, if we say tan of theta equals sine of theta divided by cosine theta, that's an identity because it's true no matter what we put in for every real number theta as long as both sides of the equation are undefined. Now, if theta happens to be pi over 2 plus any multiple of pi, okay, or another way to say it is odd multiples of pi over 2, then that turns out to be, both sides actually turn out to be undefined. But otherwise, when it is defined, both sides are defined and they are equal, so that is an identity. On the other hand, if we say when is cosine of theta equal to 0, that's not always true. That only happens in the unit circle when x is 0, and that happens at pi over 2 plus multiples of pi, so pi over 2 minus pi over 2. Or another way to say that would be odd multiples of pi over 2. So when it's pointed straight up or straight down the x-axis for the terminal side. So that's only true for certain ones. In this case, it's actually an infinite number of values of theta, one for every number n, any integer n you can put in there. But it's still only true for certain ones. So this points out the fact that conditional equations in trigonometry tend to have infinitely many answers, whereas equations in some of your algebra classes probably only had 1 or 2 or a few finite number of answers. But identities are true for everything, or at least everything where they're defined. Now let's look at some specific identities. Let's go back to where we were defining circular trig functions and remember our general definitions. There they are. And the first thing we can have are some reciprocal identities. Okay, and these are pretty straightforward. Cosecant of theta is 1 over sine of theta. Sine of theta is 1 over cosecant of theta. And this is easy to see from the definitions. If we wanted to actually prove this, okay, cosecant of theta equals 1 over sine of theta. We want to prove this. So we start with one side. This is given. And it equals 1 over. Well, sine of theta is y over r, where xy is a point on the terminal side of an angle measuring theta in standard position. So once you have that, and of course r equals the square root of x squared plus y squared. You put all that together with this, that's the definition of sine. So in other words, this is definition of sine is the reason for that. Okay? Well, 1 over r, we could take this, for example, and multiply top and bottom by r. This is the fundamental equivalence property of fractions. Okay, see my sloppy writing, you see why I type everything. And so this is r over y, and that is the, because that's just simplifying, and then this is cosecant of theta by definition. So notice I've been able to give a series of steps. I give the reasons for those steps. I start with one side and end with the other side. That's how we prove an identity. Well, the proofs of these identities are really straightforward, just like the one you just saw. They basically just go down to write everything in terms of x, y, and r, and do a little very simple algebra, and it simplifies out this way. So secant and cosine are reciprocals of each other. Cotangent and tangent are reciprocals of each other. As long as both sides are defined, these are true, and so these are identities. Notice that cosecant of theta is undefined when sine is equal to 0. Sine is always defined. So we get some, so for some particular theta values, one side or the other of this might be undefined. Secant of theta is undefined when cosine is 0. Cotangent is undefined when tangent is 0. Tangent is undefined when cotangent is 0. So there are some places where things are undefined, but everywhere they are defined, these things are equal. So they're identities. We call those the reciprocal identities. We also have a couple of what we call quotient identities. So tangent of theta is sine theta over cosine theta. Let's do a proof of that. Okay. Tan theta equals sine theta over cosine theta. Here's a proof. Okay, so again, we need some setup. Let xy be a point on the terminal side, terminal ray of the angle measuring theta in standard position. So the angle's in standard position. This is the thing. R is defined to be square root of x squared plus y squared. Of course, that's the distance to the origin. So now, with that setup, we need that setup for this. Let's start with the more complicated side, complicated looking side, and turn it into the other side. Sine of theta over cosine theta. Well, sine of theta is y over r. Cosine theta is x over r. So this is definition of the reasons over here are over here. So we have some steps here, or conclusions, and some reasons, or justifications over here. And this is the definition of cosine. So we use the definition of sine and cosine so far. Now I'm going to take this and multiply top and bottom of this fraction by r. And we know we can do that by the fundamental equivalence property of fractions. Abbreviating a little bit there. The r's cancel out, and we get y over x. And that's just some, that's a cancellation property, or just multiplying fractions. And then finally, y over x equals the tangent of theta, and that's the definition of tangent. And so we started with sine of theta over cosine theta, which was equal to this, equal to this, equal to this, equal to this, and so the beginning and end must be equal. And we have proved, we're done, we proved this theorem, this identity. Okay, in a similar manner, you can show that cotangent of theta is cosine over sine. Let's do another one. Okay, if I go to this inner angle one, you can see another one here. Okay, we've got some Pythagorean identities. Cosine square theta plus sine square theta equals 1. 1 plus tangent square theta equals secant square theta, and cosecant square theta plus 1 equals cotangent square theta. Okay, so why are these true? Let's start with the red one first. Remember, on a unit circle, if we place everything on a unit circle, what do we have? We have the x and y coordinates are cosine of theta and sine of theta if the angle is theta. Okay, and all it is just the Pythagorean theorem applied to this reference triangle. Now remember, the sides of this reference triangle are the absolute value of x and absolute value of y. Okay, and so we square those, we get absolute value of x squared plus absolute value of y squared equals 1 square on the unit circle. So x squared plus y squared equals 1. So that says cosine square plus sine square equals 1. And this is just a different way of writing that. When we write any number up here except for -1, it's interpreted as a power. It really means the proper way to write it is this right here with the parentheses. Parentheses cosine, parentheses of t, close parentheses square, but we shorthand the notation by putting the square there. So this means take the cosine of t, take the input t, find its cosine, and then square it. Plus, same thing for sine. Okay? Now, how do we get, so that proves the first one. Do you see why this is called a Pythagorean identity? It comes from the Pythagorean theorem applied to that unit, that reference triangle on the unit circle. Okay? What about this other one here? How do we get, we can get from the red one to each one of these other two very easily. So if we've got cosine square of t plus sine square of t equals 1, just divide both sides of the equation by cosine square of t. Of course, that distributes on the left to give you two fractions. 1 over cosine square of t is 1 over cosine of t squared, which is secant squared. Cosine square of t over cosine square of t is 1. Sine squared of t over cosine squared is sine of t over cosine of t quantity squared, so that's tangent square. Okay, we can also see this. Remember, I showed you the additional ways of looking at these here. Look at the triangle here that goes from C to A to D, the blue interior triangle. Now, if we just do the Pythagorean theorem on that triangle, we also get the same result here. It's 1 square plus tangent square equals secant square, and you can see that Pythagorean identity on that triangle. In a similar manner, if we start with cosine square plus sine square, cosine square of t plus sine square of t equals 1, divide both sides by sine square of t, and the sine squares cancel out here to get 1. The right side is 1 over cosecant, or cosecant square. 1 over sine square of t is cosecant square of t. Cosine square of t over sine square of t is cosine of t over sine of t squared, quantity squared, so that's cotangent of t squared. And we can see that one is the Pythagorean theorem applied to this other triangle with kind of the brownish interior there. This leg is cotangent t, this is 1, so cotangent t, cotangent squared plus 1 equals cosecant square, and we get that. And so now we've seen the proof, and you can see it visually in this particular illustration, and we could also get it from, we can also get these two from the first one. So what I do is, it's best if you memorize as much as possible in this class, but on the other hand, for the long term, if you're just memorizing stuff, you're likely to forget it. So what I do is I try to remember what I need to remember long term. Well, I need to remember long term cosine square of theta plus sine square of theta equals 1. That's very fundamental. So that's our fundamental basic Pythagorean identity. And I know I can get these other two very quickly from this. If I forget, I know I just need to divide both sides by cosine square to get one of them, and divide both sides by sine square to get the other one. And so I know how to derive those other two very quickly. And that allows me to work that out. So I don't have to necessarily memorize this picture here or this picture here to try to get things to work out, even though you can see those as Pythagorean theorem applied to those two triangles or that third triangle there. Just remember the one from there. Okay, we'll go over some more identities in our next video.